In this video, we look at problem solving related to Chapter 10. We're going to focus on Lewis dot structures. As we discussed before, we need to know the relative atom positions before we begin. And we have a basic rubric for arranging the atoms where the central atom is the low electronegativity atom. Here's our procedure for making Lewis dot structures. You may want to print this out when you're first doing these problems so you have a sequence of steps. Once you get comfortable, you probably will not need this. First, you place all the atoms in the chemical formula in their appropriate positions, like we looked at on the last slide. Then we calculate the total number of valence electrons in the molecule. We draw a single bond between each connected atom. Then we put the remaining electrons in lone pairs on each atom to give octets, and we start with the outer atom. If the central atom does not have an octet at this point, when we've used up all the electrons, then we'll need to move outer lone pairs into double bonds with the central atom. At this point, we calculate formal charge for each atom. Once we've identified that we have octets for everything and the formal charge has been minimized, we look to identify any resonance hybrid structures that may be present. We'll start off with the molecule OF2. This is oxygen difluoride. As we do these problems, you may want to stop the video and get yourself some scratch paper and see if you can come up with a solution to the problem before we go through it, and then you can check your answer. Oxygen difluoride is a little bit of an unusual molecule in that oxygen is the low electronegativity atom, and it goes in the center of the molecule. This is the atom arrangement for OF2. The two fluorines are on the outside and the oxygen is on the inside. We can calculate the total number of valence electrons in this situation. The one oxygen atom brings in 6 valence electrons. That's the 2s2, 2p4. And then the two fluorine atoms bring in a total of 14 electrons, 7 each. The valence electron configuration for fluorine is 2s2, 2p5. So that gives us a total of 20 valence electrons in this structure, and the Lewis structure will need to identify locations for all 20 of those electrons. First, we make a bond between each of the fluorines and the oxygen. That requires 4 electrons. After we use these 4 electrons, we have 16 remaining valence electrons, for which we'll need to find a location in the molecule. We start at the outside atoms, the fluorine. They'll each need 3 lone pairs. And if we do this, we see each of these has 3 lone pairs, leaving 4 electrons that go into 2 lone pairs on the oxygen atom. If we look at this, then every atom in this molecule has an octet. This is the best representation using simple Lewis structures. Next, we'll look at the molecule H2CO3. This is carbonic acid. Carbonic acid forms when carbon dioxide in the atmosphere dissolves in water. Carbon is a nonmetal, and nonmetal oxides are acidic. So carbon dioxide is mildly acidic material, and you will notice this when you drink carbonated water. Slight burn you feel is from the carbonic acid that's present. Here we have the atom arrangement with the carbon at the center, the 3 oxygens, and then the hydrogens on the outside. We can count up the valence electrons here. The 3 oxygens give us a total of 18 electrons, 6 for each atom. The 2 hydrogen atoms give us 2 electrons, 1 for each atom. And then carbon has its 4 valence electrons. This adds up to 24 total valence electrons in the carbonic acid molecule that we need to position. Next, we connect each atom with a single bond. There are 5 bonds here. That's 10 total electrons. Taken away from the 24 we have to begin with, that gives us 14 electrons that remain. So we can take these 14 electrons and begin putting them in lone pairs on the outer atoms, and they'll go on the oxygens. So in this case then, we use up all 14 electrons on the oxygen atoms, and we have 0 remaining. So here's a first order Lewis structure that has used up all the electrons, but it's not the best representation. And one of the keys, the carbon does not have an octet. In order to give carbon an octet, we take one of the lone pairs on the oxygen at the bottom, and we move it into a bond between the carbon and the oxygen atom to give it a double bond. So for our carbonic acid here, we can calculate the formal charge of each atom, and we remind ourselves of the equation we saw from our prior video. The formal charge of an atom is the number of valence electrons for that atom in the free state minus the sum of the number of lone pair electrons plus the number of bonds to that atom. Let's do the calculation for each atom in this structure. For carbon, we have 4 valence electrons in the free atom. There are no lone pairs on the carbon in this system, but there are 4 bonds to it, 2 single bonds and 1 double bond. So carbon has a formal charge of 0. The oxygens that have a hydrogen attached to them, we can calculate their formal charge as 6 for the number of electrons in the valence shell for the free oxygen atom. We subtract off the 4 lone pair electrons, and then we subtract off the 2 bonds. That gives us a formal charge of 0. And finally, the oxygen that is doubly bonded to the carbon, we see 6 for the number of valence electrons minus 4 for the lone pair electrons minus 2 for the bonds. That gives us 0. If we go back up one slide, we notice that the structure at the very in the middle, so the one on the bottom looks good. The one right up from that has an octet. You can calculate formal charge on that bottom oxygen atom, and that bottom oxygen atom has a formal charge of -1. That is the reason that we pulled the lone pair off of that oxygen atom, to eliminate that formal charge. So this is the best representation, and it gives us a good picture of what this molecule looks like. And we do have evidence that one of the oxygens is doubly bonded to carbon, while the other 2 are singly bonded. Next, we have the molecule HNO. It's a little bit of an interesting molecule. It's a little unusual. We would not have a simple naming sequence for it. It's typically called the nitroxyl species. And nitroxyl has nitrogen at the center. The hydrogen is bonded directly to the nitrogen, and so is the oxygen. This is the arrangement of atoms, and that had to be determined experimentally. So this is known. So from this, then, we can derive a Lewis dot structure. First, we have our valence electrons, 6 for carbon, or 6 for oxygen, 1 for hydrogen, 5 for nitrogen, giving us a total of 12 electrons. We make a bond between each of the atoms. That requires 4 electrons. We have 8 remaining. We place those in lone pairs. And that uses up all of our electrons. In this case, though, we notice that nitrogen does not have an octet. As nitrogen does not have an octet, we can take one of the lone pairs on oxygen and slide it into a double bond. When we do that, we end up with this structure, every atom having an octet. Now, if we go back up one step here, notice the oxygen atom. The oxygen atom has 3 lone pairs and a single bond. That's a very common structure that you'll run into in many Lewis structures. That oxygen has a formal charge of -1. The 6 for the normal atom, -6 for the lone pair electrons, -1 for the bond gives us a -1 charge. And so if the molecule does not have a net charge of a net negative charge somewhere on it, then this is something you'll typically need to get rid of. And of course, that gives us the nitroxyl molecule having this structure. If we look, every atom now has an octet with hydrogen with its 2 electrons. And we can go through and calculate formal charge. For the nitrogen atom, we have the 5 valence electrons on the free atom. That's 2s2, 2p3. We subtract off the 2 lone pair electrons and the 3 bonds, and that gives us a formal charge on nitrogen of 0. Oxygen, for the lower structure, has a formal charge of 0 as well. 6 free atom, 4 for the lone pair electrons, and 2 for the 2 bonds. And then the hydrogen has 1 - 0 - 1. So that's a good structure. Next up, we have another polyatomic ion, ammonium ion. Ammonium ion has the nitrogen in the center surrounded by the 4 hydrogen atoms. So on this, we can do our electron count. Our total valence electrons are given by the following equation. We have 4 hydrogen atoms for a total of 4 electrons, 1 nitrogen atom for 5 electrons, and then the 1 positive charge, which indicates we have 1 fewer electron in this system. When we're missing an electron, we end up with a positive charge. And so we subtract 1 from this, and we end up with 8 total electrons with which we're going to work. Now we can take the 8 electrons and put them in 4 bonds, connecting each hydrogen to the nitrogen atom. That leaves us 0 electrons. And here we have very little flexibility because we've used up all our electrons and there's no double bonds to work with. One way we finally designate this is we also need to put this structure in brackets and put a positive charge to indicate that it is actually a cation. So it's important to do this, to put the cationic representation onto this system. Doing our formal charge count, nitrogen has 5 valence electrons in the free atom. There are no lone pairs and 4 bonds. That indicates the nitrogen has a +1 as the formal charge. The hydrogens have 0 formal charge. In this case, we have to have a formal charge somewhere because the molecule is a polyatomic ion. As a polyatomic ion, it has a charge somewhere, and in this structure, we've identified it onto the nitrogen. Next, we look at another polyatomic ion, HSO3-. This is hydrogen sulfite, or bisulfite, as it is sometimes called. In this case, the sulfur is the central atom, and the oxygens surround that central atom, and the hydrogen attaches to one of the oxygen atoms. We can count up our valence electrons. The 3 oxygens give us a total of 18 electrons with which we have to work. We have 1 hydrogen atom, which gives us 1 electron. We have a 1 minus charge. So that means we have an extra electron somewhere because we have a negative charge on this system. So we put another 1 in. And then the sulfur atom brings in 6 electrons for its 3s2, 3p4. This gives us a total of 26 electrons with which we'll be able to work. So now we can do our atom connections with our single bonds. When we do that, we have 4 bonds that total to 8 electrons. So we subtract 8 from our 26, giving us 18 electrons. These 18 electrons then need to be put into lone pairs. We put lone pairs on the singly bonded oxygens. We only put 2 lone pairs on the oxygen that has a hydrogen in it because we don't want to go past an octet for any of the period 2 atoms. And that leaves 2 electrons remaining, and they will go on to the sulfur. So here we've used up all of our electrons. If you look at each atom has an octet. But this representation is not the best representation. We can calculate formal charge to convince ourselves of this. The sulfur has a formal charge of +1. There are 6 valence electrons in sulfur. There are 2 lone pair electrons and 3 bonds, giving it a +1 charge. The oxygen with the hydrogen atom on it has the formal charge of 0. The other oxygen atoms have formal charges of -1. And the hydrogen has a formal charge of 0. Now there are 2 oxygens that have a formal charge of -1, and they're right next to the sulfur, which has a formal charge of +1. And that's generally an unfavorable structure. Opposite charges on adjacent atoms are not likely to occur because the opposite charges will attract, and the electrons will typically move such that that formal charge goes away. So the way we do this is we take one of our singly bonded oxygens and take one of its lone pairs and put it into a double bond with sulfur. And so we can do it like this. If we take the bottom oxygen atom, rotate one of those lone pairs up into the double bond, we end up with this structure. And for this case now, we see sulfur now has 6 valence electrons minus 2 lone pair electrons minus 4 bonds. Sulfur no longer has a formal charge. The oxygen with a hydrogen bound to it has a formal charge of 0. The hydrogen atom itself has a formal charge of 0. The doubly bonded oxygen now, the one at the bottom, has a formal charge of 0. The only atom with a charge is the singly bonded oxygen, and it has a charge of -1. And that's acceptable because the ion itself has a net charge of -1, and that charge has to go somewhere. So it goes onto the singly bonded oxygen atom on the left-hand side of this structure. Now at this point, we need to ask ourselves why we chose the bottom oxygen atom. We equally well could have chosen the oxygen on the left-hand side of the structure. If we look at the very top structure, the 2 oxygen atoms that have only 1 bond, and they're bonded directly to sulfur, and they don't have any hydrogens on them, those oxygen atoms are equivalent. Neither one's different than the other. And so if we're going to choose to make a double bond, we can choose one of two ways. And anytime we can make a structure using two equivalent approaches that are equally good, we have a resonance structure situation. So here we see that we can use either the bottom oxygen or the one on the left-hand side to eliminate the sulfur formal charge. And in doing so, we recognize that the electron, the extra electron, that charge, must be delocalized across those atoms, those two different oxygen atoms. So in a sense, each of the oxygen atoms that doesn't have a hydrogen on it should end up having a formal charge of -0.5. The charge is shared equally between those two. And their bonds to sulfur will also be 1.5 bonds. So we see we have resonance structures. Also note, sulfur has 4 bonds and a lone pair. It has 10 valence electrons. It's got more than an octet. It has an expanded valence shell. And that structure is the best representation of the monohydrogen sulfite ion, and it agrees with experimental data. Finally, we have the molecule iodine trifluoride. Iodine is our low electronegativity atom. We put it at the center, and we have 3 fluorines around it. Now, at this point, then, we can calculate total valence electrons. We end up with 28, 7 from the iodine, and then 21 from the 3 fluorines, 7 each. We make single bond connections between each fluorine and the iodine, leaving us 22 electrons remaining. Those 22 electrons can be thrown into lone pairs. We start off with the fluorines. Each of them gets 3. Fluorine cannot go beyond a total of 8 electrons. It's a period 2 atom, so it will not go beyond an octet. The iodine, on the other hand, can, and so that takes 2 lone pairs. The iodine in this case then is going to have 3 bonds and 2 lone pairs. That's a total of 10 valence electrons. And this is the best representation of this molecule using simple Lewis structures. This is the one that agrees best with experimental data.